Hello.
Hi, I am Rachel Mickelson, and we are Group P working on the macroscopic Cilium appendage model for Dr. Bailey.
I'm Laura Barber.
And Isabella Mers.
And I'm Wilson Roan.
So our revised project statement is that the goal of this project is to develop a macroscopic model of the cilia appendage in a realistic testing environment for the model. The model should be created with materials that effectively replicate the material mechanical properties of the appendage in the human body. Additionally, this testing environment should mimic the viscous fluid that surrounds the cilia in the human body for more accurate testing. The fluid's flow should be parallel to the model, but opposite in direction on either side of the model, and these forces will allow us to either prove or disprove Dr. Bailey's theory of dynamic instability as the driver of cilia motion. So, a cilia is a tiny hair-like appendage that lines your respiratory tract. Its diameter is on the scale of nanometers and it's microns in length, and it oscillates back and forth to move debris and other unwanted particles out of your respiratory system. So it's very important for keeping your airways clear, which is one of the reasons that we want to study it. Anatomically, it's made up of doublets, which are located concentrically around the center of the model, and so we also want to replicate that anatomic structure in our model. So the main theory for cilia motion is the dynamic instability theory, which is analogous to a flag waving in the wind. So it basically means that the cilia is responding to the fluid flow past it, and that fluid causes it to eventually oscillate out of control. So our model has no drivers on it. For instance, it doesn't have any motors other than the pump. Previous models include motors, so that's one thing that we didn't want to include, so we could focus on the dynamic instability theory. Additionally, we have a model or an environment in which to test our model that has been improved from previous models. In the past, the model has been tested on both a table and an air hockey table, and these are inferior testing environments because the friction between the model and the table doesn't allow for proper oscillation. Additionally, it's in air instead of water, which is not the proper viscosity for testing. So we want to exclude both the friction and also the motors from our model.
As Rachel was saying, one of the things we wanted to focus on with our model was creating the correct environment and having no motors driving the motion. One of the other things that Dr. Bailey wanted to focus on was having the correct mechanical and material properties for cilia. So in order to do that, we dynamically scaled the microscopic actual cilia into a macroscopic version using a dimensionless parameter found by Dr. Bailey, and we ended up finding that based on the given parameters of the microscopic cilia, the correct material to use for our tubing was silicone rubber, and the correct diameter of the tube should be 3 millimeters and the length should be 2.2 feet.
So in order to create this model, we ordered all of the parts online, also 3D printed a couple pieces and got some stuff at just like local home and goods stores. So the first thing that we bought were the silicone rubber tubes. So these are those 3 millimeter in diameter tubes. In total, there are 7 of them to model those doublets that Rachel discussed earlier. And in addition to that, they run through these hexagonal spacers, which were 3D printed in order to kind of keep the individual tubes separated. As you can see, they're attached to this T-splitter at the top that we bought at a local home and goods store. And what that allows us to do is pump water through the large tube, split it into 2 of the individual tubes, and go down into the U shapes here at the bottom. Now those U shapes at the bottom are there in order to create those forces and that dynamic instability that Rachel was talking about earlier. So the forces, or the theory behind dynamic instability is that there are forces down one side of the cilia appendage and then opposing forces up the other side of the appendage. So how we and Dr. Bailey decided to try and model that force was through running water down one side and up the opposing side of our model.
Alright, so Wilson just talked about our model, and obviously it's got to go in some sort of environment for testing. Here's our environment. This environment's more portable than ones have been in the past. So previously Rachel said they used an air hockey table or just like a table. Obviously more portable than an air hockey table. Our tank here is 3 feet tall and 8 inches in diameter, so that it's long enough to hold the cilia, which is like 2.5 feet long, and it's wide enough so that there's room in case the cilia oscillate, it won't hit the sides and interfere with it. Also, it's clear so that you can see movement or whatever the cilia does in the tank as it's being tested.
So one other part of our environment that's important is the pump, and the pump here is used to pump water through the little tubes of the cilia and through those U-shaped bends. So in order to find the correct pump that we needed to use, we had to calculate the force needed in those tubes, and then from that calculate the flow rate that was necessary. And we calculated the force needed in those tubes by using another dimensionless coefficient or dimensionless parameter found by Dr. Bailey. And we calculated that force to be about 3.3 newtons per meter. And then we were able to take that force and solve for the flow rate using both laminar and turbulent calculations. And we found out that laminar flow would not be possible, but using turbulent flow, we would need a flow rate of about 18 gallons per hour through the tubes to create oscillations.
All right, so just discussing the environment a little bit more specifically, I'd like to kind of jump into the individual components. So the first thing here is the pump, which Laura was discussing a little bit earlier. This pump is typically used in like a lot of different like home aquatic systems. It's rated for 140 gallons per hour, which is significantly larger than that 18 that we calculated to be necessary. Within the environment itself, there are 2 core pieces of acrylic. One is this 8-inch in diameter acrylic tube. An additional component is just like a base plate. Then we went about attaching those. So in order to seal these 2 things together, we first used a PVC to PVC bonding material that's used in a lot of plumbing, and then used a bathroom tile style caulk to make it watertight. In addition, we just made some supports out of wood that we epoxied to prevent any bending stiffness from creating any issues. Then lastly, as you can see here, we discussed the viscosity being an important component. We filled it with just water. That will be, obviously important for not only keeping our calculations consistent, but also for ease of use for Dr. Bailey in the future. If he's to bring this around to different locations, he'll be able to easily fill it with water rather than needing some more complicated liquid with a different viscosity.
So our 5 performance goals mainly revolved around keeping the model watertight and the performance of the cilia itself. So our first 2 had to do with some calculations. So we wanted to maintain the same viscoelastic constant and be within 10% of that when scaling the model up from the microscopic to the macroscopic version. And then secondly, we wanted to make sure that the model would maintain the proper bending stiffness, as that is very important for oscillations. And so for both of those, we wanted our model to be within 10% of the actual cilia, and so we just verified that through the calculations that Laura talked about previously. Our second 2 performance goals have to do with the model and the environment being watertight, and so we just verified this by, as Wilson talked about, applying that PVC to PVC sealant and using the caulk around it, as well as making sure that any spillage that we did have could be cleaned up with 1 standard paper towel, which was both of which were achieved. And then our last performance goal was that the model should be able to sustain oscillation in response to the fluid flow for at least 5 seconds. So we weren't able to achieve that due to the lower rate of the lower flow rate of the pump that we got, and some other things, but we think that we can achieve that in the future.
All right, so I'm just going to quickly discuss how we actually went about attaching the model to the environment. So how we put everything together, and then how we just went about running our testing. In addition, I'll kind of discuss those last 3 performance goals Rachel mentioned. So one of our performance goals was to create a watertight system, which our system is, and it also does not have any spillage in testing, which is another one of our performance goals. So we'll jump into how the model actually works. So Here you can see we just plug in the pump that we bought, attach the model to this top plate, which we 3D printed, and we run a few of the remaining individual doublet tubes through it. And then water flows from the pump all the way down through the model and out the bottom. So although we did not produce the oscillations that Dr. Bailey was looking for, we were able to successfully create flow. So as you can see here, because the flow rate is not high enough, as we mentioned earlier, to create that 18.1 gallons per hour, we are in fact inducing flow. And in theory, bumping this up with a larger pump, if that was within our budget, would help us create those oscillations that we are looking for. So although we didn't create those oscillations, we did make some significant progress for Dr. Bailey in his lab. Number one, we created a frictionless environment, which is really something that he was looking for and will be important for his work going forward. And in addition to that, we were able to scale up a model to have the correct bending stiffness and the correct anatomical structure, meeting our other performance goals so that he and his lab can take this work further and then continue to try and further understand the movement of the cilia.
Okay, so we ran into a few problems when we were building our environment and the model. The first problem was that when we originally tried to epoxy the acrylic tube straight to the base and fill it with water, it wasn't quite stable enough and we had more spillage than we wanted. But we fixed that the second time around by using the PVC connector, the caulk, and then the supports. And the second problem that we run into is that the flow rate we're getting from our pump is not actually that 18 gallons per hour that we need. When we measured it, coming out of the tubes, we're only getting about 1.5 gallons per hour, which isn't enough to produce the oscillations. So we would probably need a bigger pump, and we would need to account for the friction and gravity that are causing us to lose a lot of that flow rate.
So then, yeah, in the future, we would want to achieve that larger flow rate. So we'd do that either through a more powerful pump or through potentially having larger tubes. One way to be able to use larger tubes would be using a product called Thicken Up to increase the viscosity of the water, so then that would account for the larger tubes. Additionally, Dr. Bailey had the suggestion that we could use dyes and put colored water through the tubes so you could see the cilia more clearly. Additionally, as you probably saw earlier in the model, it's really hard to tell what it's doing from the side because of the distortion from the curvature of the tank. So it'd be nice to have some sort of viewing window that's flat so that you can clearly see what's going on. And then in order to prevent more problems with the seal from happening, we'd like to use Weldon, which is a chemical seal, to bond the tank and the base, or the tube and the base of the tank together so that it wouldn't malfunction again.
Thank you guys so much. Once again, my name is Wilson Roan.
I'm Rachel Mickelson.
Laura Barber.
Isabella Merce.
Thank you.